So, hello and welcome back to our channel. And today we are going to look at polygons in a more serious manner. So, we are going to look at what is a polygon, sides, vertices, and diagonals of a polygon, angles, some property of a polygon, some of exterior angles of a convex polygon, and examples for exam prep. So, let's get started. So, basically, a polygon is a simple closed curve that is made up of entirely line segments like these, is a polygon. So let's look at what are the properties or different components of a polygon. So let's look at the side vertices and diagonals of a polygon. So a line segment forming the polygon, say AB or BC, CD or ED or EA, all form side of a polygon. So let me write that down. AB, BC, CD, DE, and EA are sides of a polygon. And the vertex are the meeting point of a pair of consecutive sides of a polygon. Say points A, B, C, D, and E are the vertex of this polygon. Next up, we have diagonals. So say AC, AD, or BE, BD, CA, CE. All these are diagonals, and these are the line segments that join the non-adjacent vertices of the polygon, and these are called the diagonals of the polygon. So in our example we have AC, AD, BD, BE, and CE, which are the diagonals of the polygon. So now let's look at some varieties of a polygon, and these can be, first look at the variety of convex and concave polygons. So let me create some examples, and then you can see how these look. So now I've created some examples for you which act as convex polygon. So a convex polygon is something for which each of its interior angles, say here, here, or here, these are less than 180 degree. So all these angles would be less than 180 degree. So then you'll have a convex polygon. Now let's look at concave polygons. So let's look at these examples. Here we have at least one of the vertex which has an angle that is greater than 180 degree. So those kinds of polygons are known as concave polygons. So in definition, a polygon in which at least one of the interior angle is greater than 180 degrees is called a concave polygon. So let's look at it at this example where we have this quadrilateral known as ABCD, for which we'll find the sum of angles of this quadrilateral. So in previous classes, you have learned that the sum of interior angles of a triangle is 180 degree. So in this example, we can see that there are two triangles. In this quadrilateral, we have two triangles, ACD and ABC. So let's find the number of the sum of the angles for this quadrilateral based on our previous information, which is the sum of angles in a triangle, which is 180 degrees. So let's get started. So our quadrilateral ABCD can be divided into triangles ABC and triangle ACD. And then we get six angles, angle 1, angle 2, and so on till angle 6. Now we'll add all these to find the sum of all the angles in this quadrilateral. So now, just to make this clear, I'll write angle 1 plus angle 2 plus angle 3 is equal to 180 degree, and this is because it forms a triangle. It is 180 degree. Similarly, for angle 4, 5, and 6, we also have the sum as 180 degree because they form the triangle ACD. So when we use these two properties, we can say that the sum of angles of the quadrilateral ABCD is equal to 180 plus 180, and that comes out to be 360 degrees. So this gives us our first property, which is sum of angles of a quadrilateral is 360 degrees. And we can do some similar tricks for, say, a pentagon or a hexagon, and we can find the value of the sum of angles for all of them. But we will not do that through, say, a diagrammatical form, but we'll do that through a formula, which makes our life a lot easier. So let me explain that to you through an example. So we have this pentagon, and we have divided it into three triangles, 1, 2, and 3. So we can calculate the total number of, or the sum of the angles, interior angles in this polygon. I'll just write this down as a pentagon, 3 into 180 degree, as given from the example above. So we can add the total number of angles in all these triangles and get the total value, and that comes out to be 540 degrees. But we can't do this for each and every type of polygon. So we need to find a formula, and we actually have a formula which we'll use in this one. So I'll show that to you. So in order to find that, we have this formula sum of. So our final formula is for a sum of measures of all interior angles of a n-sided polygon, and that is given by n minus 2 into 180 degrees. So for our pentagon, we know that n is the number of sides, which is n equal to 5. So we'll use this formula to calculate the value of the sum of angles, and it would be the same. So for pentagon, n equal to 5. So sum would be n minus 2 into 180 degree, or 5 minus 2 into 180, which comes out to be 540 degrees. And that's the same as what we calculated over here. So this becomes a very clear formula and very easy to use.